Welcome to this video on some work I've been doing recently, trying to look at how to combine a MAIHDA analysis with a regular RCT analysis. So clearly, if it's not clear what MAIHDA is, or it's not clear what an RCT analysis is, perhaps other videos are for you. But should you know what both these things are and want to facilitate them together, then here are some initial thoughts. So, okay, and what I got here is a little bit of a working document for illustrating this. So essentially, we're going to reanalyze very famous data from the 1980s, which is the Tennessee class size experiment, sometimes called Project STAR. And essentially, back in the late 80s in Tennessee, 79 schools signed up for this trial. And then with their new cohort of kindergarten children, those kids were randomly assigned to either a small class or a regular class within each of their schools. It's a little bit more complicated than that, but that's the essential premise. And of course, what they wanted to know, researchers, was is there some kind of benefit on students' maths and reading scores at the end of kindergarten if they were educated in a small class setting with only 13 to 15 kids in the classroom versus a regular one with 22 to 25 kids. So it's a randomized controlled trial. Kids are randomly assigned to those classrooms. The teachers are randomly assigned. But if you do the RCT with one school, it's just underpowered, grossly underpowered. So you need many schools, and that makes it a multi-site class RCT. So if we think about the simplest multi-level model to answer the standard research question, is there some kind of benefit of being educated in a small class? We're going to have a three-level model: students within classrooms within schools. Let's take maths as the outcome, the end of kindergarten. We're going to regress it on an intercept and a dummy variable for being a small class, which is a level 2 characteristic of the class. And so the coefficient beta 1 is going to quantify what is the effect size. So to make things easy, I've standardized the outcome. So we're in standard deviation units when we look at beta 1. We've got school effects, class effects, and student residuals to take into account the dependencies in the data. So what we get out is that beta 1 is a statistically significant 0.19 of standard deviation, which is decent in educational research. So the researchers would be very happy with that, and indeed they were. But because MAIHDA is about intersectionality and about whether you get differential outcomes or differential effects for different intersections or sociodemographic characteristics, we want to start leaning into that. So what about subgroup effects? So reanalyzing the data, we've got kind of the gender of the kids, are they male or female students, their ethnicity. I'm only really working with white and African-American Black students here because the numbers of Hispanic and American and Pacific Islanders, all this kind of stuff are very low. So and it's just a kind of a proof of concept. So it is very simplistic, but we've got a 2-category ethnicity variable. I wanted some kind of measure of SES. There is a measure of whether the kids are on free lunches. Now, some of these kids, and we can track them actually longitudinally across the first 4 years of kindergarten. Some are always on free lunches, so I call those the poor. Some are never on free lunches, and very crudely, I call those the higher SES or the rich. And then you've got some who are occasionally on free meals, sometimes not. Then I have one more variable, age. Kindergarten is very important whether you're old in the academic year. Those will be the ones born in the autumn versus the summer. Okay, potentially in a lot of educational studies. Okay? Is it important here? We'll see. But the point is that the treatment effect might differ for males and females. Is the benefit of being educated in a small class 0.19 for both males and females, or does it differ? Is it 0.19 for both white and Black students, or does it differ? And so on. Okay, so we're creeping towards doing a MAIHDA, but we're going to keep it conventional. We're in the 3-level setting, and let's just check out gender. So if you want to see where does the beneficial effect of being in a small class play out equally for males and females, you'd put in a dummy variable for being a female student. You'd interact that with a dummy for being a small class. The level 1 variable, level 2 variables, a cross-level interaction, and beta 3 is the moderating effect. So it's basically the difference in the benefit of being in a small class between males and females. Now, if you fit the model and get the results out, what I find, and these are all results by maximum likelihood estimation at this stage, The treatment effect for males is 0.23 of a standard deviation, whereas for females it's 0.14. So that's a sizable 0.08 differential, which sounds very meaningful, but in this particular data set is not statistically significant. Now, it probably would be if you ignored the clustering, but I've taken into account the clustering here. Yeah, no evidence actually of subgroup effects there with respect to gender. Let's repeat for race, SES, and age. We can do that now. Treatment effect for white students, 0.19, which suggests for black students it was 0.17 there. Some kind of rounding to do decimal places, but effectively no significant difference, smaller differential than the gender gap. SES, there is a gradient. Okay, so the most affluent, the most affluent students, or the ones who are never on free lunches at least, the benefit of being in a small class is 0.22 of standard deviation for them, whereas it's only 0.15 if they are always on free lunches. So, but again, that's not significantly different. So this is kind of a proof of concept, kind of in terms of how you mechanically do this analysis, rather than being an application which really sells the benefit. Effectively, it's underpowered. It wasn't designed to do this degree of subgroup analysis. After the overall effect of a small classroom, we're trying to get more out from the data. Really, you need a bigger data, I think, to do this. But let's carry on. We've got the age effects. These are not coming out monotonically, so there's not really much going on with age. The treatment effect kind of bounces around, but not significantly different. Perhaps in Tennessee, kids could start, I'm not sure, I'm not an expert on Tennessee education. You might tell from my accent. Also, it's from the late 1980s when I was a child myself. So it could be that kids didn't all start at the beginning of the academic year as they do in England. So yeah, okay. But anyway, for this teaching example, no significant differences. So this is not really very a great application for an intersectional MAIHDA on the RCT, but I can show how it's done. So with those four, where are they? Those four variables up there, gender, race, SES, and age. We've got two categories, 2 and 3 and 4. Okay, 2 by 2 by 3 by 4 is 48. Okay, so there are 48 combinations of sociodemographics. Widths down here, yeah, there you go, 48. Strata, you might call it intersections, you might call them strata. So we want to know what is the treatment effect in each and every stratum. For each and every combination of sociodemographic characteristics, I've got some kids in a regular class, some in a small class, and so I can do that mean difference. But I do it in a multi-level setting with all the benefits of accounting for dependency, shrinkage, and so on. Highly unlikely to given the results so far, that this is going to work out, but let's give it a go. So we want to add stratum as a level, as a set of random effects to the model, because we want stratum-specific treatment effects. We've already got classroom random effects and school random effects. And so this turns the model from a 3-level analysis into a cross-classified model. Okay, so what we got here is, excuse the rather unconventional notation. So I'm sticking with my IJK for student I in class J in school K, but I'm now putting S subscripts on the intersect and the all-important slope coefficient, the treatment effect on being educated in a small class, because I'm allowing those coefficients, those stratum-specific coefficients, to vary across the 48 strata. And so here are my strata effects. And so the thing of interest now is, once again, the overall treatment effect, which we know is around 0.19 of a standard deviation, but crucially, how does that now vary to give intersection-specific effects, 48 of them? So we're going to do that. Zoom on a bit more now. Unsurprisingly, when I try and fit that by maximum likelihood, I don't get very far. Effectively, the stratum variance on the treatment effects, the variance of these across the 48 strata, is stuck on 0. Okay, and it's stuck on 0 because there's very little variation in the treatment effect across sociodemographic characteristics. We know that. We know that from the simpler analysis we did. Okay, in the conventional subgroup analysis in the multi-level setting, I found no gender effects, no race effects, no SES effects, and no differential age effects. So yeah, it's not surprising when I go for all 48 intersections and a fine-grained thing that also there I'm going to struggle to find variation. And so the variance gets stuck on 0. Now, it won't be zero, it will be something. So, you know, this is also a kind of limitation of perhaps the maximum likelihood framework or the estimation method here, that it gets stuck on zero, whereas the true value will be small but not zero. So, you know, one thing you could do is you could flip over to MCMC, and with the benefit of priors, that will mean it's not stuck on zero, but then you could argue the priors doing an excessive amount of work. Okay, so there are debates around that. But anyway, I can fit this model by MCMC. The variance is no longer stuck on zero, and I can at least show you what the results would look like. Here we go. Here are the 48 intersections, a league table for the treatment effect size. Remember, the average is around whatever this is, 0.17, 0.18, 0.19, whatever it is. I now got 48 effects, one for each combination of characteristics. You can see those up there. So it is white males who are never on free lunches, so the more affluent families who are actually occupy the top 4 effects. Okay, so there's clearly a gender by ethnicity two-way interaction in this structure, which is kind of beneficial. Those are groups doing well. Okay, so it's not just gender, not just ethnicity, but the combination. Now, at the opposite end, I see a predominance of always free lunch. Okay, at least the bottom 4 are always free lunch, and so you know, that's coming out. We did see an SES gradient, remember, earlier, whereas the more affluent had a bigger treatment effect. So that's playing out here as well. So we're seeing some of the same things we saw earlier. Okay, but we do see variation in general from a low of about 0.11, 0.11 maybe, up to a high of something like 0.25. So I am seeing variation. But when it comes to looking at the individual precision of a treatment effect for any given intersection, we've got very wide confidence intervals. Okay, there's not that much data per intersection. I'm cutting it 48 ways. I've got school effects, clustering, and classroom effects, which reduces the information in the data. So very wide confidence intervals, and indeed only this set are kind of individually coming out as significantly positive benefit effects, where we've got a majority of intersections are actually overlapping with zero. Okay, so I'm kind of cutting the data finer than it really allows. I don't really have the power to do what I'm trying to do, even though substantively it's sensible to be wanting to do this. I need a bigger data, is what this is saying. But there is some hinting, there is clearly some structure, which I mentioned. This isn't just noise or randomness. There is structuring signal in this league table. Carrying on, now MAIHDA model 2 puts in those explanatory variables, just like we did above, actually, but I did it separately. I first put in gender, took it out. Then I put in ethnicity, took it out. Then I put in SES, took it out. Then I put in age, took it out, right at the beginning, just to look at the conventional way of looking at interaction effects. Now I put in all of those simultaneously, and that will give me kind of differential treatment effects across the 48 intersections, but according to this kind of additive structure. Okay, there's no kind of two-way interactions involved in these treatment effects, but there is, and this is where the MAIHDA comes in. Okay, so this random effect here on the treatment effect is mopping up all possible two-way, three-way, and four-way interactions between my 4 sociodemographic characteristics: gender, race, SES, and age. And so that's kind of speaking really to the intersectional argument that there might be something nuanced going on at particular intersections which we can easily miss. So that's what this is doing. Okay, so let's have a little look. What we get out are, first of all, the same kind of plot we had before, which is just the predicted treatment effects for the 48 intersections. It looks pretty similar, but one thing which is different is I've got a wider range now. It's from around 0.05 up to 0.3, whereas before it was more, what did I say it was before? 0.11, I think I was saying before. 0.11 up to around 0.25. So the wider range is because I got those additive effects sitting in the specification for the intersectional stratum specific treatment effect. I'm adding in this kind of structure which does most of the work, and the shrinkage in the means which I'm plotting is towards that additive structure. And there's far less shrinkage than before, because I'm not shrinking to the single overall treatment effect of 0.19. I'm shrinking to the specific implied treatment effects by additivity. So there's less shrinkage, there's more variation. And so that leads, yes, to more variation and to wider confidence intervals than before. Okay, I'm getting kind of back to a more of a kind of a fixed effects type approach here. So again, with more powerful data, this would be more beneficial. These would tighten up, and these would typically be considered more reliable predictions of the treatment effects because you're putting that additivity in. But remember, the additivity is not significant. None of those effects are really individually significant. So, because it's underpowered. So there is something going on, but we're not really able to kind of state it with a degree of confidence that we want to or need to by conventional statistical rules. And so we're being, it's just a demonstration of how to do this. That's all this is. Okay. Now the final plot here are these interaction effects, these two-way, three-way, four-way. We've got a single value for each and every intersection for how the predicted treatment effect for that intersection deviates from what we'd expect based on additive structuring of gender, race, SES, and age. And this is hinting at the presence of two and higher way interactions, because these deviations, they range from around 0.03 negative to 0.03 positive, a 0.06 range of a standard deviation. That's meaningful. So I've got variation, and but the issue is, again, that I can't really pick out any or talk about any intersection in isolation, because the confidence intervals are so, these are 95% credible intervals with this Bayesian, but they're so wide, because the data were collected for a particular purpose, getting the headline intervention effect, not for getting this highly nuanced 48 separate intervention effects, where you clearly need bigger data set, and your power calculations would have to be amped up really to do this properly. But mechanically, hopefully you found that interesting as how to take MAIHDA beyond what most people do, which is simply a description of how mean outcomes vary across intersections. We've now shown how to do how do treatment effects vary across 48 intersections from an RCT, not any old RC, but a multi-site cluster randomized controlled trial. Okay, so yeah, I'm going to do lots more work in this area. So hopefully that was interesting. And by all means, contact me, drop me an email if you want to talk more about this kind of work. Thank you for listening.